morning everybody. Hope you're all healthy and safe. Today we are going to begin with a new chapter. The chapter is chapter 6 about self-adjoint operators. Okay, so in this lecture we'll be discussing about what is self-adjoint operator, and we'll study few properties related to that. Okay, so let's see the definition. This is a definition. We call an operator A, a bounded operator A from edge to edge, is said to be self-adjoint or symmetric. Okay, if and only if for every x comma y belongs to H, we have inner product xay is equal to inner product axy. So for any operator and for every element in the space H, if this equation is satisfied, that is inner product xay equal to inner product axy, then we say that the particular operator is self-adjoint or symmetric. Okay, so it's just a simple property. Now let's see the first one, that is the point spectrum of a self-adjoint operator satisfies the condition, that is sigma of p is contained in R. That is, if we are considering the operator, the point spectrum of a self-adjoint operator. Okay, so if you are considering the point spectrum of a self-adjoint operator, then the point spectrum will always contain only real numbers. So that is the first property. So let's see how we can prove that. It's a very simple proof. The properties can be proved very easily. So first of all, we will consider an element in the point spectrum. So let lambda belongs to sigma p. So if lambda is an element of sigma p, then I can say that a of x is equal to lambda x, where x is not equal to 0, right? Now inner product ax x will be equal to inner product xax, right? Why? Because A is self-adjoint. So we are considering the self-adjoint operator. So inner product axx will be equal to inner product xax for every x. Okay, so I'm going to replace this ax by lambda x. So this will be inner product lambda xx is equal to inner product x lambda x. Now let us use the property of inner product. Lambda is a constant, so I'm going to take this out. So lambda into inner product xx is equal to, when I take the constant or the scalar from the second variable, it will become a conjugate, right? Lambda conjugate will be equal to inner product lambda conjugate into inner product xx. Now you can see that both of this can be cancelled, or you can replace this by norm. So from this, what do I get? I get lambda is same as lambda conjugate. So for a complex number, if its corresponding conjugate is also same, that means the imaginary part must be 0, right? That is, it will be a purely real number, belongs to the set of reals, right? So that was our need, that is, we wanted to prove that the corresponding operator, that is the corresponding elements of the point spectrum, will always be real, right? So the point spectrum of a self-adjoint operator is consisting of, or it always contains, set of real numbers. That was the first property. Now let's see the second one. If lambda 1 and lambda 2 are two numbers, or are two eigenvalues such that lambda 1 is not equal to lambda 2, okay, are such that is they are eigenvalues. So ax1 is equal to lambda 1 x1 and ax2 is equal to lambda 2 x2. If this is true, then x1 and x2 will be orthogonal. That is the property. It is, we are given two eigenvalues. So the operator A is self-adjoint, okay, in all these cases that we are dealing. A is a self-adjoint operator, and if you are given two eigenvalues, then corresponding eigenvectors, that is if we have x1 and x2 such that ax1 is equal to lambda 1 x1 and ax2 is equal to lambda 2 x2, then x1 and x2 will be orthogonal to one another. So let's see the proof how we can do this. This is also very much simple. Now we have let us see, lambda 1 into inner product x1 x2. This can be written as, I am taking the scalar inside, that is inner product lambda 1 x1 x2. Now lambda 1 x1 can be replaced by inner product ax1, right? It's given in the property ax1 x2. Now since A is self-adjoint, I can write this as x1 a x2, right? But this means I can replace a x2 by lambda 2 x2. So this by the property of inner product, I'm going to take this lambda 2 out common, and I get this as inner product x1 x2. So I get lambda 1 inner product x1 x2 is equal to lambda 2 bar x1 x2. Now this lambda 1 and lambda 2 are completely distinct, right? So there is no possibility that lambda 1 and lambda 2 can be equal, because here we are considering lambda 2 conjugate also, but they cannot be equal because lambda 1 and lambda 2 are not equal. So if this has to satisfy, that is lambda 1 inner product x1 x2 is equal to lambda 2 bar inner product x1 x2, then the only possibility is from this we get inner product x1 x2 equal to 0, that is x1 is orthogonal to x2. Such a simple proof. So if you are given, that is if you are given any two eigenvalues, then the corresponding eigenvectors will be relatively orthogonal to one another. That was the second proposition or second property that we have discussed right now. Now let's discuss another property. Before that, we have to discuss a definition about invariant subspace. Okay, so we are given a space H, and a subspace L of H will be said to be invariant with respect to the self-adjoint operator if with respect to an operator. Okay, this is not specified for self-adjoint, this is true for every operator. So we are given a space H, a subspace is said to be invariant with respect to an operator if A acting on that subspace L, A of L, is contained in L itself. That is, whenever that operator acts on elements in the subspace, that operator, the resultant, will again be an element in the subspace L itself. Okay, so that is what is meant by invariant subspace. So next is the property relating the invariance and the self-adjoint thing. So the property is the third one, that is if L is invariant corresponding to a self-adjoint operator, then its orthogonal will also be invariant. Okay, so that is if we are having a self-adjoint operator A, if A of L is contained in L, then A of L orthogonal will also be definitely contained in L. Okay, that is the third property. So let's see how we can prove this property. So for that, we will be considering an element in the orthogonal space, okay, and one in our, let y belongs to L orthogonal and x be another element of L. Okay, now x is an element of L and L is invariant, right? It is invariant corresponding to A, the operator A. Now if x belongs to L and L is invariant, means A of x is an element of L itself, right? So A of x is an element of L. Then if I take the inner product of A of x and y, what will happen? A of x is an element of L, y is an element of L orthogonal, so their inner product will be 0, right? This is true for every x. Now since A is self-adjoint, I can write AXY as XAY. This is also 0, right? So I can say that AY is an element of L orthogonal. Why? This is true for every x, right? So for every element in L, inner product of that every inner product of an element in L and AY is always 0. That means AY is an element of L orthogonal. So Y was an arbitrary element of L orthogonal, and I got A of Y to be an element of L orthogonal. So this implies I can say A of L orthogonal is contained in L orthogonal, right? So that was the proof of our third property, that is, if we are considering corresponding invariant subspace or corresponding to the self-adjoint operator, then the operator or then the space orthogonal of that space will also be a invariant subspace. So these were the definition, and we discussed about what was self-adjoint operator, we discussed what is invariant subspace, and we discussed few properties. There is another property which I would like you guys to just work out, the fourth one. It is given in your textbook, so just go through it and just try to work it on your own. So that's it. Thank you.